course or video in abstract linear algebra. This is video 1 on complex numbers. This corresponds to chapter 1 and section 1 of the textbook. Now, we're going to talk about complex numbers before getting into linear algebra, just because a lot of things that we do with linear algebra just kind of work better when it comes to complex numbers rather than real number coordinates. And that has to do with, famously, a polynomial. If it has degree n and is non-constant, it will always have precisely n solutions in the complex numbers. And that's right, you can say something similar but not quite as nice when it comes to the real numbers. But for the complex numbers, it just works perfectly. And a lot of linear algebra relates to polynomials. And so hopefully that just gives you at least a sort of glimmer of an idea of why it's better to situate, especially for this topic, to situate things in the complex numbers. So let's go ahead and define what the complex numbers are. A complex number is any ordered pair. So, right, fundamentally, they are ordered pairs of real numbers. We will typically write the ordered pair AB as the, A plus BI. And then this set of complex numbers is just denoted by this double struck C symbol, very similar to how we denote other number sets. But this does not fully define the complex numbers, right? If this were the definition of the complex numbers, then they would be no different than pairs of real numbers, and that just can't be the full story. We wouldn't have a whole special name for that. Part of what it is to be a complex number is the definition of how we add and multiply them. So let's talk about how do we add some two complex numbers. Well, of course, we coordinate-wise add the numbers. We refer to this as the real part. So there's, A and C are the real parts of each of these complex numbers. And so the sum of the two complex numbers has real part equal to A plus C. They have imaginary part B and D. When I say imaginary part, I'm talking about just the real number B, just the real number D. I'm not including I in that. And so when we add these two complex numbers, it has imaginary part equal to B plus D. So this is the definition, right? So although that plus symbol right there looks the same as this plus symbol right here, they are in fact different. This plus symbol in between the real part and the imaginary part is kind of just a notation, right? It's just a different way of writing the complex number. This plus is in fact the complex number sum, right? You've got a complex number on the left, a complex number on the right. This is how you sum those two complex numbers together. So, usually it doesn't matter to distinguish these things, right? We write it this way just because it's natural to think of all of this as just, we've got these various numbers and we're just talking about the same concept of addition throughout. But technically speaking, they're not the same. But anyway, we don't need to dwell on that too much. The point, right, if you don't totally get that point, it's not a big deal. It probably won't affect your understanding of anything here. Anyway, so we have also a definition of how you multiply some two complex numbers. And again, we're going to specify what it does for the real part and the imaginary part. So if you take A plus BI, that's one complex number, take another complex number, C plus DI, we are multiplying them together, and I want to tell you what complex number results. And I will do that by first telling you what its real part is. In particular, its real part is given by this formula, AC minus BD. And its imaginary part is given by AD plus BC. So that tells you what the number is. Of course, right, if you did sort of just pretend as if all of the additions all kind of meant the same thing, and right, like you just pretend like I is just a legitimate number or something. Like you would think that you can just multiply this out, right? You'd take a plus bi times c plus di. You'd operate from the fundamental understanding that I squared is -1, like you would, right, if you were trying to do this kind of in a more sort of common sense rather than as such an abstract presentation of this. You'd start from the idea that I squared is -1. You'd assume that you can kind of put I together with other real numbers in natural ways. You would distribute A so that you would get AC plus ADI plus BCI and then plus BDI squared. And then you would use the fact that I squared is -1. You'd group together your real parts, right? So this would be -BD. We would put that together with this pure real number, and that's where you would get AC minus BD. The imaginary part would come from the middle terms. You would factor the I out, get AD plus BC with an I on the outside. And you can kind of think of this as like, this is where the definition comes from, is just thinking that I should work in these ways. But if we're being very abstract and very formal, then technically this is how you define things in an official codified mathematical definition. And this, right, so now that we have defined all of these things, right, only having defined multiplication, at that moment, that's when the complex numbers are truly defined for us here. As a matter of a little bit more notation, if you take any real number, we kind of want to, talk about being able to take a real number and putting it together with other complex numbers. But from everything that we said, all you can do is put two complex numbers together. You can't put a real and a complex number together. Well, here's kind of how we resolve this tedious technical concern. When we write the real number I, what we really mean is the complex number with imaginary part equal to 0. And that makes it a complex number. And now, given the definitions of everything involved, you can take this real number, which is actually a certain kind of complex number, and now we know what it means to add it to some other complex number or to multiply it with some other complex number and so on. And likewise, right, same trick when it comes to having a pure, we often call this like a pure imaginary number, AI. That seems like a real number times the number I, which we haven't officially accepted as a number all on its own. But the trick is, of course, that we just interpret this as actually being the complex number with real part 0 and imaginary part A. And of course, I, all by itself, technically is not an accepted symbol. It's not a complex number, but we just take this to be shorthand for real part 0, imaginary part 1, and now it's an accepted symbol. Okay, let's discuss briefly some properties. Hopefully most of this is familiar. I'm not going into great depth because I assume that anyone viewing a course on math this advanced has probably seen complex numbers before, so anyway, like I said, we tend to think that I squared equal to -1 is like the defining feature of I. Here in this abstract and formal presentation, that is not a first principle. It is actually derived from the definitions of multiplication and so on that we laid out earlier. So this is a derived fact, not a first principle about what I is. It is easy to verify that addition is associative and commutative and has an identity element 0 for complex numbers, where here lambda is any complex number. Likewise, multiplication is associative, commutative, and has its own identity. I suppose I didn't write that, so I guess I should. Oh, division. Division is associative, commutative, and has its own identity 0 for complex numbers. Likewise, multiplication is associative, commutative, and has its own identity. I suppose I didn't write that, so I guess I should. Oh, division is associative, commutative, and has its own identity 0 for complex numbers. Likewise, multiplication is associative, commutative, and has its own identity 0 for complex numbers. Likewise, multiplication is associative, commutative, and has its own identity 0 for complex numbers. Likewise, multiplication is associative, commutative, and has its own identity 0 for complex numbers. Likewise, multiplication is associative, commutative, and has its own identity 0 for complex numbers. Likewise, multiplication is associative, commutative, and has its own identity 0 for complex numbers. Likewise, multiplication is associative, commutative, and has its own identity 0 for complex numbers. Likewise Yeah, I should do that now. So the number, right, the so to speak real number 1, which of course we actually understand to be code for the complex number with real part 1 and imaginary part 0. Anyway, has this property that if you take any complex number lambda, then 1 times lambda is equal to lambda. You are encouraged to verify that using the definition of the multiplication of two complex numbers, but I'm not going to do that. I think that's a fairly elementary exercise. So if you have any questions about it, leave a comment and I can address it. But I think probably most people can handle that. So I'm not going to be too explicit about that. But so we have an identity for multiplication, right? We have this number 1, which when you multiply lambda, it leaves lambda as it is. There are also inverses, right? Inverses for all addition, right? If you take any complex number alpha, there always exists a beta such that alpha plus beta is equal to 0. That makes alpha have additive inverse beta here in this example. There are also multiplicative inverses for all non-zero complex numbers. So if alpha is a non-zero number, then there exists a beta such that alpha times beta is equal to 1. Now that actually, right, so proving this claim that every alpha has an additive inverse, that is a pretty easy thing to demonstrate, and I'm going to let you do that, right? That's an exercise for you. But this one's maybe a bit harder, and so I'm going to go ahead and show you why this is true, right? For all non-zero alpha, there exists a beta such that alpha times beta is equal to 1. That's what I'm going to prove to you. And so that's what's here. Now, I'm going to prove it kind of in stages, right? Because like, where do you begin? Well, maybe what you sort of think about is if I have any given complex number alpha, and here I'm going to say that alpha is equal to a plus bi. Well, we would like, to find some other number such that the product gets you 1, and, when you're thinking about in some sense, I guess what I have to do is I have to get rid of I, right? I mean, maybe I have to do other stuff too, but if the result I'm aiming for is the number 1, it would be great if I could see how I could multiply by something that gets rid of I. And so let's just kind of start with that as a slightly easier sort of intermediate goal here. And what you might be familiar with is that the conjugate, right? If you take any number, a plus bi, and multiply by its conjugate, then, and by the way, the conjugate is just where you take the imaginary part and flip its sign. So if the sign used to be plus, now it's minus, and vice versa. So anyway, if you multiply by the conjugate, kind of the middle terms cancel, right? So if you work out all the arithmetic or algebra or whatever you want to call it, and you distribute this out and simplify everything down, you will find that the result is a squared plus b squared, right? So multiplying by the conjugate is the way to eliminate I. Now, that doesn't mean that we're yet at the number 1, but maybe that gives me a helpful idea. Maybe if I then take kind of a minus bi and divide that by a squared plus b squared. Well, right, there, the kind of idea is I know that when I do the top part, right, when I multiply a plus bi times a minus bi, that's going to come out to a squared plus b squared. If I'm then further dividing by a squared plus b squared, then the result is going to be equal to 1. So that, right, so the claim here is that this number, right, this a minus bi all over a squared plus b squared, that is the inverse number, right? That's this beta that I was talking about earlier. Well, actually, I won't write it here because I've already written it here, but, right? And so let's write it in terms of its real part and its imaginary part so that we're very explicit about that. The real part is a over that a squared plus b squared, and the imaginary part is the negative b, again, right? If you think of it as kind of like distributing the a squared plus b squared into this difference up here. That's a useful way to think about what's going on here. So anyway, so you get these coordinates, and that is the multiplicative inverse. So there it is. There is my demonstration that this thing is in fact a true claim about the complex numbers that we had defined above. Now, as a bit more notation, and I should probably sort of indicate that this is some notation here. If beta is the inverse of alpha, then we typically write it as negative alpha, right? So negative alpha just means the additive inverse of alpha. And we could write, alpha plus negative beta, or really we could write any number. We could write gamma, any arbitrary other number, plus negative beta, right? That would be the gamma plus the additive inverse of beta. That's what that means, but we usually use the more familiar and simpler notation of gamma minus beta. They just mean the same thing. So in fact, this is the notation that is getting defined right now. By very similar sort of thoughts, the multiplicative inverse of alpha is typically written as 1 over alpha when it exists, right? Assuming alpha is not 0, of course. And again, right, like we can sometimes write the product alpha times 1 over beta, but we tend to prefer the shorthand notation alpha over beta. Now, if you have any collection of objects, right, any collection at all of any kind of objects, and there are some operations, and here we're going to write them as plus and times because that's how we think of them, but they really, right, like all we're saying is that they're operations. We don't know what they really mean. You just have a collection of objects, you have these two operations on the objects, and if those operations are associative, commutative, they have identities, that plus has inverses, times has inverses for non-zero elements, and if times distributes over plus, which by the way, I think maybe I didn't say up above, but that is another property that the complex numbers have, is that multiplication distributes over addition. What that means is that if you take any complex numbers, alpha, beta, gamma, and then alpha times beta plus gamma is always equal to alpha beta plus alpha gamma. So that's just what it means for multiplication to distribute over addition. By the way, obviously, I am often omitting the explicit multiplication symbol. You can include it, you can omit it, we all know what it means. So just a point about notation there. But anyway, so when you have a collection of objects and they satisfy all of these properties that we've already discussed, then we call such a collection a field. That is just like the word we use to summarize a collection of objects having all of these properties. So Q, the rational numbers, is a field because it has these operations plus and times, right? We can add rational numbers, we can multiply rational numbers, addition is associative, commutative, and so on. It has all those other properties. So Q is a field. R, the real numbers, is also a field. I'm going to assume that that's familiar from like a real analysis course or something. Well, here we're learning from all of what we've said so far that the complex numbers also forms a field. It's worth knowing that, for instance, the 2x2 matrices, right? Like let's think of some examples which are not fields, right? It's always nice to see examples, but it's also always nice to see non-examples to know kind of where the boundary is for things that are and are not fields. So let's take the set of all matrices, 2x2 matrices. This is not a field, and one of the easiest ways to think of any reason why it's not a field. Actually, let's think about what's the first thing in our list of things this must satisfy? Does it have a plus operation? Yes, it does. We have a good, sensible way of taking some two matrices and adding them together, right? So you've seen that earlier in an earlier linear algebra class or something. And does it have a multiplication operation? Well, since they're all 2x2 matrices, then you can multiply any two of them together, because specifying that they're 2x2 means the dimensions always match. Okay. Is multiplication and addition, are those both associative operations? Yes, they are, and that's something you can check. Maybe we'll check that later. But what about commutative? Now, addition is commutative, right, for 2 by 2 matrices. But multiplication is not. So that's like the first property that fails in the example of 2 by 2 matrix multiplication. It is not a commutative operation. There are matrices. So here are 2 matrices, right? We can call this, I don't know, matrix big A, matrix big B, and this is them swapped around in a multiplication. And if you work out the computation, then you'll see that AB results in 1, 0, 0, 0, like that. BA results in 0, 0, 0, 1. Not the same matrix, so multiplication does not commute. So this is an example of, right, like 2 by 2 matrices are not a field, in part at least because multiplication fails commutativity. Now, like, if we just continue checking the conditions just as a nice, like, exercise, there are identity elements, right? Addition has the 0 matrix as the identity element for 2 by 2 matrices. Multiplication has the identity matrix, right? Ones along the diagonal, zeros everywhere else. That's the multiplication identity matrix for 2 by 2s. And addition has inverses, so that's good. What about multiplication for non-zero elements? That is to say, is it always the case that you can take some non-zero matrix, that would be a non-zero element in this example, is there always an inverse of a non-zero matrix? Famously, the answer is no. I'll let you write down an example, but the answer is no. So there's kind of a second reason why 2 by 2 matrices do not form a field. But then does multiplication distribute over addition? Yes, famously that is true for matrices. So there's just like a confirmation of which properties 2 by 2 matrices have. We can see that it has some of them, actually a lot of them, but not all of them. So there you go, right? There's a non-example of a field, the 2 by 2 matrices. Now let's see one more. And, you know, like we see like these number sets, Q, R, C, they're so familiar. What about Z, the integers, right? Is the integers an example of a field? No, of course I would have written it if it were. No, the integers fails to have inverses, right? I think, right, like let's think about this. For integers, is addition and multiplication associative? Yes. Is it commutative? Yes. Do they have identities? Yes, the numbers 0 and 1 for multiplication, right? 0 for addition, 1 for multiplication. Does addition have inverses for have an inverse for everything, right? Yes, because if you take any integer, then its negative is also an integer, and that's its additive inverse, so yes. The integers have additive inverses, so it has that property. What about multiplicative inverses? I shouldn't write a check, it's a cross, because no, because there are certain non-zero elements, like for example the number 2, which does not have a multiplicative inverse. There is no integer which when multiplied by 2 results in 1, so that means that the integers do not have multiplicative inverses, and so they're not a field, right? So that's what, in a sense, that's kind of what makes Q a field when Z is not, is that Q is kind of furnished with all of those inverses for non-zero elements, right? Multiplicative inverses. So anyway, okay, so there's the idea of a field. Often we're going to want to be somewhat agnostic, right? Like a lot of the things that we're going to talk about when we're multiplying matrices, when we're doing this and doing that with various matrices, we'll need a field. It'll be important that we have a field, but it won't really matter which field most of the time, right? Like only at certain moments in studying linear algebra is it really going to even matter which one we're talking about. Therefore, we're going to abstract away which field we're talking about. The book says that it'll just be R or C, but most of the time, it could even be Q, right? But so in order to be kind of, indifferent to which field we're talking about, because it won't really matter, right? What we say will be true no matter which field we're dealing with, then we'll write this double struck F for an abstract field, right? So double struck F could mean Q, R, or C. The book, though, really just talks about R and C. Now, in the theme of further being explicit about various notation, if we have a field element A, and if we have a natural number M, then A to the M is going to mean multiplying A with itself M times. It's the familiar definition of exponents. Immediate from this definition are some facts. I won't prove them. They should, they have kind of tricky proofs. Proofs are often require breaking into many different cases about like whether M and N are like both positive and I guess never mind, because we are restricting to just talking about the natural numbers. So maybe the proof is actually just really simple and really direct. It's a counting argument, right? Basically what, in this case where we can simply do an argument by counting, because here we're saying that the exponent M and N, right? I guess I should also remark that N here is also another natural number. Then, this is just a counting argument, right? A to the M just means M copies of A. If we then take N copies of those M copies, then how many A's do you have altogether? M times N. It's a kind of a fundamental counting principle that if you have N bags, each of them containing M apples, let's say, how many apples do you have? M times N, right? So by a simple, right, especially because these are the natural numbers, we're not talking about negative exponents, and that's a really simple argument. And by a relatively simple argument here, we can show that AB to the M is equal to A to the M, B to the M. That's like distributing the exponent. What's the argument? How do we know that this is true? It's a pretty simple argument. You get M copies of AB, right? So you go AB, AB, and you do that AB, AB M times. But then you can take each of the A's, group them all together, and this is due to commutativity, right? I am essentially using commutativity and associativity, but glossing over those details because it's not that important. Fundamentally, I can rearrange the terms, and I can put all the A's together. And if I put all the A's together, well, since I have M of them, then that's the same thing as A to the M. Then I put the B's together. In fact, they'll already be together because, right, once I'm done putting the A's together. So then you get B to the M, and that's the argument.